Hi, my name is Monica, and in this video I'm going to tell you a little bit about multiplicative group of integers modulo p. This group is very important for Diffie Hellman key exchange and Gamal digital signature. This is the group that we use in those protocols. So if we want those groups that we want to use, they use prime numbers. So if we have multiplicative group of integers modulo p, p is prime number, this is the type of groups we want to use. So what we have here, we have a set of elements. We have elements from 1 to p minus 1. And we have group operation, this operation defined on this group. This is multiplication modulo p. Modulo p. So there are a few important things about this group. So this group is closed under multiplication modulo p. What it means, if we take two elements from this group and we use this operation on those elements, we have a guarantee that the result is still in the group. So if I take two elements, so for every two elements from that group, the result is also the group. So that's the first thing. Then we have identity element exists there. And of course, it's 1, like for regular multiplication. If we multiply 3 elements, let's say A, B, C, this would be congruent to if we multiply A, B, C. So order of multiplication doesn't matter. So first you can like multiply those two elements, or you can multiply first A and B. It doesn't matter. We still have the same result. Because we have this identity element, also for we have some inverse elements. In fact, for every single element, we have the inverse element. So for every element in that group, there is an inverse. So what it means, for every element A, we can find its inverse such that the result of this multiplication is congruent to 1 modulo p. And another important property is here that, in fact, we can change the order, so we can do this, kind of like swap A with B. So those are like basic properties of this group. There is another important thing about this group, that we can talk about generators of such groups. So what it means to be a generator, it means that it has to generate entire group. So we say that number G another name for the generator is primitive root modulo p, and actually you can see it in books about cryptography. So it is a generator for every element. for every element, let's say every element E in group, we talk about the specific group, there is an integer exponent, in fact, such that if we take this generator, there exists some kind of k that will give us as a result this element E. Everything, of course, modulo P. So then, if for every single element in group we can find such k, then we say that G generates entire group. Okay, so as an example, we can check this group with P equal 5. So we have elements here 1, 2, 3, and 4. We have multiplication modulo 5. And let's check G equal 2. So G to power 0 modulo P, this gives us 1. G to power 1 modulo P is in fact 5. That gives us 2 square modulo 5. That gives us 2 square, that gives us 4. So we have 4. And then we have 2 power 3. So 2 to power 3, that gives us 8 modulo 5, so we have 3. So you see we have all those elements, so it generates 1, it generates 2, it generates 3, and 4, all elements in the group. So it means that 2 is a generator of multiplicative group of integers modulo 5. Of course, for cryptography, we want to work with bigger groups. Sometimes it's hard to find generator of entire group. Sometimes, in fact, we don't really need a generator of entire group. But what we want, what we need is a generator of a large subgroup. Okay, so what are possible sizes of subgroups of such multiplicative groups of integers modulo P? Well, there is certain rule there. So the size of subgroups, the possible sizes of subgroups are divisors of P minus 1. So, in other words, the order of subgroup is the number of elements in the subgroup. So if we have this group and those orders, they are equal to the factors of P minus 1. Okay, so going back to our previous group. So for this group, okay, so what we have here, we have a subgroup generated by 1. So 1 only generates size generator and subgroup. So if we have generator 1, it generates only once, right? Because 1 to every power, that gives us only once. So this is size 1. If we take 2, as you could see, this is size 4. It generates entire group, and the group is a subgroup of it itself, always. If we take generator 4, number 4 generates a subgroup of size 2, so it generates this subgroup. Okay? So those are possible sizes. So 1, 4, and 2. So P minus 1 is equal 4. So we can divide 4 by 1, 2, and 4 only. So that's why those are possible sizes of subgroups. If you're looking for a large subgroup, we can write some kind of very simple program, and we can have a look at other numbers. But before we will do that, if you saw my other video, you remember that we worked with P equal 83. So P minus 1 is 82. Factorization of 82. 82 we can divide it by 2. We have 41. This is prime number, so 41 gives us 1. So it means that multiplicative group of integers modulo 83, this group has only 3 possible sizes of subgroups. So it's either 1, it is 2, it's 41, and so yeah, 4, and entire group. So 4 possible sizes of subgroups. Okay, so say, of course, 1 will generate a subgroup of size 1. Generator size and subgroup. So generator 1 generates subgroup of size 1 with just 1. 82. Now, there is a rule. P minus 1 always generates subgroup of size 2. And we have 1 and P minus 1 there in our case, this is 82. Like here before, you can notice that before we had this other subgroup and 4, which is P minus 1 generates subgroup of size 2, 1, 4. So that's one of the rules. And in my other video, we used 7. And in fact, you can see that 7, you could see that 7 generates subgroup of size 41. And here we have like a lot of elements, and we can actually generate them with Python. Okay, so I'll stop sharing whiteboard. Okay, I will just use simple idle. It will be kind of easier. So what we have a prime number P. We have generator, we call it G. And then we want to generate all elements. So what we basically do when we generate numbers, we multiply G times G, then modulo P, then again times G, modulo P, and so on. But in program, we have to remember the original G. So we keep generating until we hit 1. Why so? So when we hit 1, it means that we go back to the beginning, right? Because we start with G, right? G to power 0 is 1, G to power 1 is G, G to power 2 is G squared, and so on. And at a certain moment, this remainder modulo P will give us 1. So it means that we kind of like are back to 1 and we start generating the same numbers. So we keep generating until we hit 1. So while number is not 1, we will do this. So we will have next element times G and everything modulo P. So this is what we will do. Now we want to just see those. So we will print. Of course, you can save it or something. This is just for like kind of idea for the video. So we will print numbers, and in this way we are out of the loop when we have 1. So we will actually not print 1 at the end. So we have to print it again out of the loop to see this 1. Okay, so P equal 83, G equals 7. So let's make it kind of nice so we can see actually what's happening. So P, and we print P, then we will print G. Okay. Just want G. Okay. And then we will print generators, elements of the group generated by G. generated by G, generated by, and here we have G. Okay. That will look kind of bad. Okay, let's try to see what we have here. So now we will run it. Yes, we want to save things here. Okay. So actually I printed one twice. So what we have here, we have those generators here. So we have 49, 1 first, then we have 11. So of course, first one was 7. So I have to move this print first, because actually we also want to print the first element. Okay. So of course, generator is in the subgroup that it generates. Okay, so here we have 7, then we have 49, 11, 77, 41, and so on, and at the end we have 1. Right, so those are all elements of the subgroup that is generated by 7. Okay, now how many elements we have there? I told you that we have 41 there, so actually we can compute it. So we have 1 here. We will not count it inside loop, and we have there number 7. Okay, so we will start with I equal 2, and every time we will enter again, we will increase I by 1, and we can print the size of it. Yes, and then we will have I. Okay, we will run it again. So it's 42. I'm sorry, I did some small error somewhere. So we should start with I equal. So it really depends where I put it. So we start with 1 here because it will count 1. Then 7 will be, okay, 7 will be counted here. I guess many programmers have issue with 1, right? I guess so. Okay, so this is subgroup of size 41. Okay, that's why it's good to know a little bit math in order to test your programs. Okay, so even if you are a great programmer, you know what to do. In order to test your code, you should know a little bit of math. Okay, so we can also check like this number 5. Okay, so I will change. So if P is 5, we already know what will happen here, right? And this is 2. This should generate a very small subgroup. Okay, so we have 2, 4, 3, and 1, and size of this subgroup is, of course, 4. Then if we will change here, so G, just if you don't believe me, I will generate just 1 element. Okay, so we have 1, and order is 1. Then we can change it to 4. I told you that it generates subgroup of size 2. And we have size of it is 4 and 1. So this is very simple code that you can actually just try to play with it and try to see what kind of subgroups you can generate. And for cryptography, of course, this P has to be kind of good, big enough, not even 83. And this is just example 83 and 7. This is what I used in my other video about Gamal digital signature. So 7 generates subgroup of order 41. So this is not like a generator of entire group. If you want to see, like if we have 29 and 2, so the size of the multiplicative group of integers modulo 29 has 28 elements, right? So for 2, you will see that this generates entire group. Okay, so we have 28. So it means that for P equal 29, Number 2 is a generator of the entire group. What it means that we can call it a primitive root modulo 29. So thank you very much for watching and have a good day.